Leonardo, empecemos.
Buenos días. Bienvenidos a la 30ª versión del Simposio Internacional de Estadística 2021. Este es un evento que cumple 31 años, solamente fue interrumpido el año pasado por motivos de la pandemia COVID-19. Sean todos bienvenidos. Para nosotros es un placer. Inma, que nos va a ofrecer la charla inaugural del día de hoy. Tenemos también el profesor Álvaro Montenegro.
¿Se desconectó quién? ¿Leonardo?
Para esta inauguración del día de hoy tenemos los siguientes puntos. Primer punto, himno nacional de la República de Colombia. Segundo punto, himno de la Universidad Nacional de Colombia. Tercer punto, palabras del decano, el doctor Giovanni Garavito. Palabras del director del Departamento de Estadística, Luis Fernando Grajales. Y bienvenida al comité organizador a cargo del profesor Sergio Calderón. Y la conferencia del profesor Pingma, Big Data Analytics Through Subsampling, que irá después de todas estas intervenciones. Entonces, primer punto, himno nacional de la República de Colombia.
Profesor, ¿nos escucha? Por favor, compartir nuevamente y compartirlo.
A continuación, palabras del decano de la Facultad de Ciencias de la Universidad Nacional de Colombia, profesor Giovanni Garavito.
Gracias. Buenos días, profesores del equipo de dirección de la Facultad de Ciencias, profesor Luis Fernando Grajales, director del Departamento de Estadística, profesor José Alfredo Jiménez, presidente del comité organizador de este evento, profesor Ping Ma, conferencista magistral. Professor Ping, welcome to the University and thanks for participating in our International Symposium on Statistics. Profesores, investigadores de nuestra facultad, invitados especiales, asistentes al simposio, amigos todos. Extiendo a ustedes un cordial saludo de bienvenida a nuestro 30º Simposio Internacional de Estadística, organizado por el Departamento de Estadística de la Facultad de Ciencias, sede Bogotá de la Universidad Nacional de Colombia. Nuestra facultad ha sido pionera en investigación científica en Colombia. Algunas de nuestras dependencias pueden trazar su historia hasta las primeras incursiones científicas en nuestro país. Actualmente somos custodios de las más importantes colecciones biológicas y arqueológicas de Colombia, activos estratégicos que el país ha depositado en nuestra institución. Pero más allá, somos centro de excelencia para la investigación y la innovación, con 195 grupos de investigación y 210 laboratorios, que son evidencia contundente de la gran capacidad de investigación en ciencias exactas y naturales, así como en ciencias farmacéuticas. Yo diría que si no todos estos grupos de investigación, la inmensa mayoría contamos con el apoyo de los investigadores de nuestro Departamento de Estadística como garante de la calidad de nuestras investigaciones. Nuestro Departamento de Estadística en el año 1984 concibió la idea de generar un evento nacional de estadística, dando origen a un escenario en el que los estadísticos se reunieran a compartir sus experiencias académicas y profesionales. La iniciativa rápidamente contó con el apoyo de las escuelas de estadística del país en esa época. El simposio fue madurando y en 1990 tomó el nombre de Simposio de Estadística de la Universidad Nacional de Colombia y en 2012, se consolidó como evento internacional que congrega anualmente a la comunidad estadística alrededor del área. El actual plan de desarrollo de la Facultad de Ciencias, lo misional como camino hacia la excelencia, ha apostado a una difusión del conocimiento pertinente en forma adecuada a los fines de la institución, para lo cual eventos como este simposio son actores protagónicos. Pero son las personas, nuestros profesores investigadores, nuestros estudiantes y el personal de apoyo administrativo, el mayor activo estratégico de la facultad y el verdadero soporte a esta gran capacidad de investigación, desarrollo e innovación que les he mencionado. Este evento da seguimiento al objetivo de contar con escenarios de encuentro y reconocimiento mutuo entre los investigadores, como una herramienta para promover el trabajo interdisciplinario en equipo y optimizar el uso de los recursos. No tengo dudas en manifestar que el Simposio Internacional de Estadística representa para la Facultad de Ciencias y la Universidad Nacional de Colombia un evento respetable y apreciado del cual nos enorgullecemos. Importantes desafíos prevé el futuro para este simposio y para la investigación en ciencias básicas en Colombia. Quizás el mayor de ellos, la urgente necesidad de una política de país frente a la investigación científica que reconozca el valor de la investigación básica como eje fundamental para el desarrollo sostenible de un país. La aproximación conjunta de investigación, desarrollo e innovación en los últimos años genera un balance pobre en lo que corresponde a la financiación de la investigación básica, que cuando debe competir con proyectos de desarrollo e innovación, generalmente tiende a ser sacrificada. Felicito a la comunidad académica del Departamento de Estadística de la Facultad de Ciencias por este importante evento, que deseo sea placentero para todos ustedes, y los invito a que consideren a la Facultad de Ciencias de la Universidad Nacional de Colombia como la casa de todos los estadísticos y un excelente aliado estratégico. Muchas gracias.
Muchas gracias, profesor Garavito. A continuación, palabras del director del Departamento de Estadística, profesor Luis Fernando Grajales.
Buenos días. Muchas gracias. Apreciado decano, Giovanni Garavito, al comité organizador del simposio, el doctor Pigma, thank you very much to accept our invitation. Nuestro simposio de estadística, como es parte de la Universidad Nacional, ha estado en más de 10 ciudades en el país durante estos 31 años del evento. También hemos tenido la posibilidad de abordar muchos temas de la estadística. Hemos podido ser apoyo de creación de nuevos programas de pregrado y posgrado en estadística. También la posibilidad de tener más revistas de estadística en nuestro país. Algunos comités científicos de estas revistas se han reunido en los simposios. Siento la felicidad también de que nuestro simposio haya servido para lazos de sesiones invitadas de la ISBIS, International Society for Business and Industrial Statistics, Biometría y otras sociedades científicas que nos han apoyado en todos estos años en el simposio. Hemos tenido, como en esta versión, invitados de alta calidad académica. Nuestra felicidad en este simposio tiene que ver con que al tener en este evento más de 200 participantes, siento la felicidad de que nuestro simposio tenga un reconocimiento, un prestigio y agradezco inicialmente al comité organizador, al profesor José Alfredo Jiménez, Sergio Calderón, Luis Hernando Vanegas, mis colegas y a Lina María, nuestra asistente del simposio, y a todo el equipo de la Facultad de Ciencias que apoya todo este trabajo del evento virtual. Les agradezco porque tenemos la posibilidad de que nos reunamos como comunidad en estadística, en todos los aspectos teóricos aplicados, usuarios de la estadística, a reunirnos, que son los momentos también que esperábamos desde hace 2 años, para presentación de trabajos de grado, de avances de investigación, de tesis doctorales, tesis de maestría, resultados de proyectos de investigación. Este es el espacio, este es el momento y quisimos revivirlo y gracias a este comité organizador que siguió adelante con esta idea. Agradecer que en los inicios, así como mencionaba nuestro decano, en los inicios hay colegas que ya no nos acompañan, ya están en el más allá, el profesor Leonardo Bautista, el profesor Jorge Martínez, y ellos entonces fueron pioneros en todo este trabajo. Queremos agradecerles también a los actuales colegas pensionados, Pedro Nel Pacheco, Oscar Soto, formaron parte de todo este trabajo del simposio, y ahora nosotros espero que en este momento Oscar, Pedro Nel, si están viendo esta inauguración, les agradecemos porque podemos seguir avanzando con esta semilla que ellos comenzaron. Agradezco a los invitados internacionales thank you very much for invited conference, for accepting our invitation to our symposium. Muchas gracias a nuestros invitados internacionales por aceptar la invitación a nuestro simposio. Les deseo los mejores éxitos, que puedan disfrutar también la parte académica. Tenemos un reto fuerte que es la parte virtual, pero así como mencionó nuestro decano, estamos listos para también enfrentar este reto y queremos en especial que como Departamento de Estadística, acá en la Universidad Nacional de la sede de Bogotá, como Facultad de Ciencias y nuestra Universidad Nacional a nivel de todo el país, queremos dar un avance en cuanto a que hay muchos procesos de investigación, de avance en la ciencia que queremos seguirlos apoyando. Agradezco a todos los asistentes al evento. Recuerden que ustedes son la razón de ser de este simposio. Muchas gracias y que puedan disfrutar toda la programación académica que tenemos en este simposio. Muchas gracias a todos.
A continuación, de nuevo, como lo han manifestado mis colegas, un agradecimiento a todo el comité organizador del simposio, el profesor José Alfredo Jiménez, el profesor Luis Hernando Vanegas y el profesor Sergio Calderón. A continuación, las palabras del comité organizador a cargo del profesor Sergio Calderón.
Buenos días. Estimado señor decano de la Facultad de Ciencias, profesor Giovanni Garavito, director del Departamento de Estadística, profesor Luis Fernando Grajales, conferencistas, profesores, Pingma, welcome to our symposium, profesor Álvaro Montenegro, cursillistas invitados, miembros del comité organizador y asistentes, muy buenos días y sean ustedes bienvenidos al 30º Simposio Internacional de Estadística. Como viene siendo habitual desde sus primeras ediciones, el simposio se ha organizado en diferentes ciudades del país, con el fin de contribuir al intercambio de ideas y experiencias relacionadas con la estadística y sus aplicaciones. El año pasado, debido a la pandemia, no se tuvo esta oportunidad. Sin embargo, con el fin de continuar con esa tradición anual, esta versión se realiza de manera virtual. Esperamos que el próximo año nuevamente sea presencial y podemos llevarlo a cabo en alguna ciudad. Inicio declarando que es para mí un honor estar frente a ustedes para dar inicio a este evento que se ha convertido en una de las principales actividades académicas de carácter nacional e internacional de la Universidad Nacional de Colombia. Pero además de ser un honor, es un gran reto porque pensar en el simposio no es solo considerar las 3 décadas de historia de un evento. Cuando pienso en el simposio, me veo obligado a recordar muchos de los desarrollos que se han venido dando en la estadística en nuestro país y que de una u otra forma el simposio ha sido puente para su difusión o conocimiento de los mismos. Ejemplo de esto son técnicas de análisis de datos textuales, la geoestadística y uno de los retos actuales en el cual esta versión se enfoca y es el Big Data y en general la analítica de datos. Debido a esto, es inalcanzable en este momento hablar de todo lo que abarca o significa el simposio. A pesar de que en esta ocasión las actividades se desarrollan en modalidad remota, esperamos que no se pierda el interés de nuestros asistentes y, como en las versiones anteriores, sea una gran oportunidad académica y social para reunirnos con personas interesadas en el mundo de la estadística. Los cursillos y conferencias aquí previstos contribuirán sin duda a profundizar en el conocimiento de la temática propuesta, mejorando la comprensión de nuestra realidad en el Big Data y, en ese sentido, ampliando la percepción de las oportunidades y los retos de futuro inmediato que, muy previsiblemente, aguardan a nuestra sociedad. Mi reconocimiento por ello a los conferencistas y ponentes que, con espíritu de total colaboración, van a participar a lo largo de esta semana con las sesiones programadas. También debo reconocer la labor de todas aquellas personas y dependencias de la Facultad de Ciencias de la Universidad Nacional que, con su esfuerzo y apoyo, han hecho posible la celebración de este simposio. Expreso finalmente mi gratitud a los distintos comités que han colaborado en la realización del evento y a los participantes en sí mismos. Me complace su asistencia. Permítame que declare inaugurado el 30º Simposio Internacional de Estadística. Muchas gracias.
Bueno, a continuación tenemos la charla inaugural. La charla inaugural está ofrecida por el profesor Pingma. El profesor Pingma es profesor de investigación distinguido de la Universidad de Georgia en los Estados Unidos. Cuenta con un doctorado en estadística de la Universidad de Purdue. Es fellow de la American Statistical Association y sus áreas de investigación son análisis de Big Data, bioinformática, análisis de datos funcionales, geofísica. Profesor Ma, again, thank you for accepting our invitation to our 30th Symposium in Statistics in Colombia, organized by the National University of Colombia. We hope you can visit us in person soon in Bogota as soon as this pandemic ends. You can start now, Professor Ma. Thank you very much. We cannot hear you, Professor Ma.
Oh, okay. I cannot start the video. Okay.
No, it's fine. Thank you very much.
Okay. Let me see. Yeah. Can you see the slides?
Yes, very clearly. Thank you very much.
Okay. So thank you for the organizer for inviting me. And it's really a pleasure to join the International Statistics Symposium. I know it's a delayed event. Originally, it was last year, but due to pandemic, and it's held this year. And my original plan is also give a short course, and I apologize because of the schedule change. I couldn't. And in the future, I hope I can share my research with you in the future events. Okay. So today I slightly changed my title. My original title is big data analytics through subsampling. Now the title is called Subsampling in Data Science, but I'm going to talk about the same thing. Okay, so let me first introduce some historical perspective and clarify the concept of subsampling. Okay. In classical statistics, subsampling is generally referred to the generalized procedure of resampling. And it's well known, bootstrap is a subsampling method. In bootstrap, each time you randomly sample the same sample size from original sample. Okay, subsampling is to take random sample of smaller size from original sample to overcome some difficulty of resampling procedure. For example, we know that in bootstrap and the resampling procedure, it requires the distribution of statistic is somehow local smooth as a function of unknown model, but the subsampling procedure does not require this. And but this is not a topic I'm going to talk about. If you really need, if you're really interested in subsampling, please refer to this monograph by Politis and Romano, published in 1992. Okay. Anyway, let me talk about historical historical perspective of classical statistic paradigm. Okay, here I use arrow to indicate the sample size or model dimension of the statistical method from small, middle to large. Okay. Traditionally, we typically have a scientific question, and we design an experiment, collect small or moderate size sample data. Then empirical or computational methods are applied to this data set. These empirical methods include model selection, model fitting, hypothesis testing, confidence interval building. Okay. After that, we typically conduct asymptotic analysis. Asymptotic analysis is typically conducted for sample size goes to infinity. And combine these two approaches together, we have a perfect classic statistic paradigm, cover a wide range of sample size scenario. Okay. And the empirical methods interpolate real data. Asymptotic analysis extrapolate the empirical outcome to infinite sample size, hypothetical data. And these two analyses, empirical method and asymptotic analysis, complementary with each other. So essentially, we live in a very comfort zone of classical statistics. However, as big data become ubiquitous, we now suddenly do not stay in a comfort zone of classic statistics. The significant challenge we have is our empirical methods were typically not designed to scalable to big data. For example, the computing environment such as R was not designed to be memory efficient and friendly. Okay, when we have a large sample, we have a significant difficulty in getting computational results. For example, the bootstrap, okay, is well known. The bootstrap is computationally intensive. Okay, for a single data set, you need to generate multiple bootstrap sample. And if this original sample is a big data, then it's very difficult to even store this bootstrap sample in the memory of a computer. Okay, this is especially problematic as the emerging field of data science is rapidly developed. In data science, the data type we frequently encounter is big data. Okay, and now let us take a look. What is data science? Okay. The widely accepted definition was proposed by Drew Conway, okay, and who is a founder of several data science solution provider startup. Okay, his background, I think he got a PhD from political science, but he's working now on data science. And this diagram was developed by him. Okay, essentially, in his definition, data science is an integration of mathematics, statistics, and computer science, as well as the domain science. Okay. However, this is not only definition of data science. Recently, there is a well-known computer scientist, a woman, have another definition of data science. This paper and his definition becomes well-known after he got this year's Turing Award. Turing Award is almost the highest award in computer science. Okay, in his definition, he said, okay, data science is just a tight integration of computer science and domain science, has nothing to do with statistics and mathematics. Okay, and this diagram was presented in one of his paper. The title is also a little bit strange. Okay, so-called battle for data science. Okay. And I think as our statistician, we always are friendly to other scientists. We are eager to collaborating with other scientists rather than battle for something. Okay, but anyway, this is an alarming message for our statistics community. If we do not try our best to solve the new problems in data science, we will lose data science to computer scientists. Okay, so when we talked about the domain science in various research disciplines, big data almost become ubiquitous. For example, in biomedical science, high throughput sequencing data becomes almost the default data types. Okay, and you can get all kinds of these data from NCBI website. In the Earth science, if you study the Earth's structure and the dynamics of especially the inner Earth, you may get the waveform data from IRIS. This is another database from Washington University out in Seattle. Okay, and if you check, I recently checked this IRIS database. The data size is already becomes a petascale. Okay, in high energy physics, if you study some new particle models, okay, you may need some data from CERN, where each second they generate a lot of data. Okay, and in internet social media, we have Twitter and Facebook. These are the streaming data I will briefly mention in the middle of my talk. Okay. And in agriculture, now there is a high throughput genotyping, also have a lot of data being collected. Okay, now let me show you a small video. Okay, these video clips show the high throughput phenotyping technology developed by my colleague in UGA. Okay, essentially the tractor mounted with a camera and the sensors to measure the crop yield, crop nutrients, crop canopy, volume, and biomass, water content, and so on. Just in a morning, we have terabytes of the data. So how to manage, analyze these data is pose a significant challenge for the data analytics, okay? And how to deal with the big data. One simple idea is use a subset of the data, okay? In machine learning, this idea has been used frequently and also used very early in their development of the field. For example, in support vector machine for classification, instead of using all data, support vector machine aims to find a subset of data which is close to the classification boundary. These data points are called support vectors. Then support vector machine constructs classification boundary, use only these support vectors. And the performance is really outstanding. It has a remarkable success in practice. And in computational geometry, there is a concept, so-called core set, okay? The idea of core set is to take a representative subsample of the regional sample. And this representative subsample is called a core set, okay? And in these slides, on the left-hand side, I illustrate there is a massive data set, and then in the right-hand side, I illustrate we can take some small sample. Okay, this small sample is the so-called core set. Okay, so essentially, this idea of taking subsample from the big sample has been ubiquitous in many fields. Okay. And then in today's talk, I mainly talk about some statistical development of subsampling in this field. Okay, in order to take to look at the problem, let us take a look at the very simple problem that is a linear regression. Okay, in linear regression, we have a response we call the Y, and we have multiple predictor x1 through xp. Okay, and then we have these coefficient beta, beta 1 through beta p, and plus this random error epsilon. Okay, and then to write this into the matrix vector format, we have capital Y equals capital X times vector beta plus epsilon, vector epsilon, and typically the random error we assume is follows normal distribution with mean 0 and independent identically the variance sigma square. Okay, and in computer science, they just talk about these problems. They talk about these large sample problem as a tall matrix, because the matrix of X, okay, here is very tall. Okay, so the basic idea of subsampling is instead of using the whole sample, we take a subsample out of this big sample. Okay, and the idea is using this subsample, we want to approximate the least square estimate. We use beta hat to denote it here. And also, we can directly use this subsample to estimate the true underlying truth. We use beta 0 to denote it. Okay, we assume there is an unknown true parameter beta 0. There is the true value of this beta is denoted at beta 0, and we can directly using this subsample to estimate this beta 0 also. Okay, so as I said, one simple idea is use subsampling. Now let us take a look at uniform random subsampling. In uniform random subsampling is that each data point has the same probability being sampled. Okay, and then I use a toy example to illustrate the point. In this toy example, I generated 2,000 data points from this simple linear regression. The so-called simple linear regression is that it only have the slope and the intercept. Okay, and the true regression line is this black line and shown in this data. Okay, in this plot. And then for simple random sampling or uniform random sampling, we take a random sample of 10 data points. Okay, of a subsample size equals 10 from these 2,000 data points. Because this is a uniform random sample, and in each run it will result in a different subsample. But now let's just try one run. Okay, in one run we got 10 data points, and I use this green star to indicate them. Okay, and then once we got these 10 data points, and I feed a least square line using these 10 data points, I got this regression line indicated by this blue dash line. Okay, and you can see this blue dash line is quite deviate from the true regression line, I generated the data. Okay. And by the way, if I use the total these 2,000 data points, I can also construct a least square line using this full sample. And then the least square line I generated using full sample is a black dashed line, and you can hardly to visualize from this plot because it's almost identical with the true regression line I generated the data. Okay, so anyway, from this plot we can see uniform random subsampling or simple random subsampling does not work very well because it has a lot of variation depending on how do you take the data, depend on which run, where you get the subsample. It could substantially deviate from the full sample. Okay. The question is why this uniform random sampling does not work. Okay. If we look at this plot closely, we can see most of the data in the center form the data clouds, but we have some so-called very influential data points clustered in the upper panel, in the upper here and the lower here. Okay, so you can see here some 3 data points here are very influential, and there are 2 data points up there also are the influential data points. These data points have a significant impact on constructing these least square regression line. Okay, so we can slightly change our idea from the uniform random subsampling to importance sampling. In the importance sampling, instead of each data point has the same probability being sampled, instead we give the higher sampling probability to those data points have substantial impact on our model fitting process. For example, the data points in the upper left corner and the lower right corner. Okay, in this simple setting, okay, we can easily identify which data points are influential data points. However, most of the time we have our predictor or X matrix have multiple dimension, okay? And we cannot simply visualize them in this 2-dimensional scatter plot. So we need to translate our intuition into mathematical expression so that we can manipulate it, okay? So one simple influential measure we use is use this so-called perturbation concept. The perturbation concept is like this. So we measure, okay, if we add a small perturbation of the data points x, yi, okay, we want to see how much changes we get for the fitted least square regression line. So this can be expressed as the partial derivative of the least square regression line of yi. Okay, this is the predicted value of y with respect to the true observed value of yi. Okay, essentially this is a perturbation concept. Okay. Interesting enough is that this perturbation concept can be calculated as following. Okay, we know that the least square line, the least square fit y hat can be written as x times the least square estimate of beta hat. Okay, which can be written as this complicated multiplication. Okay. And eventually we can write as this height matrix times y. Okay, this height matrix is essentially this x times x transpose x inverse x transpose. Okay, and then we can write this as this following expression: yi height equals hi1 times y1 and so on and so forth. And then for the previous, the proposed the influential measure, okay, if we take a partial derivative of yi hat with respect to yi, we just get HII. HII is diagonal elements, is II's diagonal elements of this height matrix H, okay? And in statistics, we call this as a leverage score, okay? And now we want to use this leverage score to as an importance sampling probability to sample data, okay? Because this HII could be bigger than 1, okay? So we take a simple normalization, that is using HII divided by the summation of this HII, okay? So the basic leveraging algorithm just looks like the following. We take a subsample of size R. R is much smaller than the regional sample size, okay? And with probability of pi I is for each data point, it has different sampling probability. And the pi I is constructed using this leverage score. And then after we get this leverage subsample, and then we can calculate the weighted least square, okay, of this subsample, okay, and the weights depend on the subsampling probability, okay. We call this beta tilde left, okay. This is a basic leveraging algorithm. Okay, now let us come back to look at our toy example, okay. Still 2,000 data points, and then we use the leverage subsampling algorithm applied to these 2,000 data points. We still want to get a subsample size of 10, okay, we get 10 data points, okay. These 10 data points, we use this right cross to indicate them. And then based on these 10 data points, we get the weighted least square line. This is this right line. And you can see this right line is very close to the true regression line we generate the data, okay? And you can run this many times and it's very stable compared to the uniform random subsampling estimate, okay? So these essentially the idea of leverage subsampling, okay? And in 2014, we have a paper essentially to study the bias and the variance of these resulting leveraging subsampling estimates, okay? And here, I don't want to talk about details, but the take-home message is that the bias is relatively small, okay? For least square, for full sample least squares, our leveraging subsampling estimate is almost unbiased. It's almost unbiased, but there is a still higher order bias, okay, in the sense of Taylor expansion, okay. If we do conduct a Taylor expansion, we find, okay, the first order is unbiased, but there are some higher order smaller terms, okay. For the variance, obviously, it has a larger variance than the full sample or ordinary least squares, but the term is also can be spelled out, okay. After that, we continue to study this problem. We want to say, okay, for different loss function, is there any so-called optimal subsampling estimate, okay? It turns out yes, okay. So our 2020 AI stat paper present a detailed analysis of this so-called optimal subsampling. For example, if we are concentrated on something so-called asymptotic mean square error, okay, so that is based on this least square, we can calculate the asymptotic mean square error, and based on this asymptotic mean square error, we want to minimize the subsample estimate error. And then from there, we construct the sampling probability. Interesting enough, we get some results very interesting. In this scenario, instead of using Lagrange score, we should use a square root of Lagrange score. Okay, there are many different interesting discovery in this paper. Okay, if you are interested, please refer to this paper. Okay, now let us move on to our next topic. Okay, that is streaming data. Okay, streaming data is really a new type of data in the sense that the data continues to come in without stopping. Okay, for example, this cartoon shows the internet traffic data. Okay, and there is another cartoon shows the internet, also the internet traffic between I think it's Asia and Europe. Okay, so there are big network and there are these data continues coming in. Okay, streaming data really pose a significant challenge for statistic community because in classical statistics we always have a sample with a finite size, but the streaming data, the data is keep on coming. Okay, and for example, in this internet traffic data is also coming in a high velocity. Okay, and some classical method, for example, in statistics we have this recursive estimation or computation. That is each data point when it comes in, we can calculate some estimate, and then when additional data comes in, we can just refine this estimate. Okay, pretty much in Bayesian data analysis, this is a so-called recursive update. Okay, however, because of this streaming data comes in high velocity, most of the time you cannot use this recursive update to do the computation because they come in too fast. Okay, once you finish your computation, a lot of data points already passed away, already passed by. Okay, you cannot capture them. Okay, so instead we develop a subsampling procedure. Okay, so in order to model these streaming data, we use a simple autoregressive model with piece order. Okay, so suppose these data follow this autoregressive model with piece order. Okay, and then our idea is that for this streaming data, we take a small chunk of data out of these big streaming data streams. Okay, that is in here. Okay, we take a small chunk here. Okay, and then once we get this small chunk, and we can apply our classical statistical method onto this small chunk, and then get our estimated result. Our hope is that the estimate we got from this small chunk is as similar as to the results we got from the bigger sample, or maybe the infinite sample from these data streams. Okay, so this is our procedure. Okay, so once these data streams start, okay, in here we show we have a small pilot sample. The pilot sample essentially gave us some idea, okay, what this streaming data looks like. Okay, we get some very simple estimate from this pilot sample, and then we let this data stream go on and on, and then once we have some we find some data points that we begin to take a sample. Okay, we let these data stream pass by, but once we decide where to start, we start to take the record of this streaming data. Okay, and we go on and until once our computer reach certain capacity of memory, and then we stop. Okay, this is the sample we take. Okay, this is the sample take. And how do we decide this where to take a subsample? Once again, we use the concept of leverage. Okay, because when you estimate when you estimate the coefficient of this AR model, you can still use a method of least squares. Okay, and then mimic what we did in the linear regression. Okay, we can still calculate something so-called leverage score. And then in these data streams, we just, in each data point, we calculate their leverage score. Okay, and until somewhere we find, okay, these data points has a very high leverage, and then we begin to take these subsample, and then subsample size is with respect to the constraint of the computer we have. Okay, if it's big enough, and we can calculate some sequential index to decide how large the subsample we can have, and if your memory is very small, and then we just take the largest possible subsample. Okay, which is largest capacity you can have. Okay, this is the sequential subsampling. Okay, we develop for overcome the difficulty of the data streams. Okay, bring to us. Okay, so this is a piece of work we have been working on the streaming data. Now let us move on to the next topic. This is a so-called misspecified model. In the previous two scenarios, okay, what we have decided is the model is already well specified. Okay, so for the first example, we know we want to do the linear regression. For the second example is we know the underlying model is AR model, is an auto-regressive model. But in reality, this assumption is not true. In reality, we may have a data set because the data is big enough, we cannot examine this data very carefully. The only naive idea is, okay, if the data is historically people fit linear regression, okay, then we may just fit linear regression. So in reality, there is a significant chance that we could misspecify the model. We specify a wrong model for the data. Okay, so here I illustrate this idea in using a simple toy example. Suppose the data is generated from this nonlinear relationship. Okay, this black line indicate that there is a nonlinear relationship between the predictor and the response. Okay, however, if we misspecify this model as a linear regression model, and then we generate data points. Okay, we generate data points using this leverage method from this full sample, and then we get these data points here, and then we fit a linear regression, and then you can see this linear regression does not capture the overall pattern. Okay, so there is a significant risk. Okay, we may get a very misleading results. Okay, if we specify the wrong model to the big data. Okay, how to overcome this difficulty? What we propose to do is using this so-called Latin hypercube design that is well-known design in the experimental design. Okay, the basic idea is Latin hypercube design is the following. Okay, in some grid point, okay, we just generate some sample, okay, and then get a sample from here, okay, and very specific type of Latin hypercube design is so-called orthogonal Latin hypercube design. It's OLHD. Okay, in this OLHD, okay, is different from these ordinary Latin hypercube design is in that is this subsample almost orthogonal, okay, almost orthogonal, okay. So essentially we apply this orthogonal Latin hypercube design to the subsampling, okay. So now let me illustrate this idea using a simple toy example, okay. So here we have a data set, okay, x1, x2, and the data cloud is showing in here, okay. And for this data set, which first generate the orthogonal Latin hypercube design, okay. These are the design points, okay. And for some design point, there is no corresponding data points associated with these design points. So what we can do is find the nearest neighbor, okay? Find the nearest neighbor sample point closest to the design point, okay? And then get this subsample, okay? This subsample is approximately of the regional design point, orthogonal Latin hypercube design, okay? And then what we have shown is that in misspecified model, and these in this design-based subsampling has a very good robust property, okay? Robust to the misspecified model, okay? So this is the third topic I bring to you guys today, okay? So now let's move to another topic. That is, we talk about, so far talked about mostly a linear model, okay? Linear regression, autoregressive model, and misspecified model. And here I want to talk about a non-parametric model, okay? In particular, we talk about a Gaussian process model. It's very simple in statistics. Essentially, we still have univariate response Y, and we have multiple predictors x1 through xd. And in non-parametric regression, we always using this arrow, these brackets to indicate that this is x1 through xd, okay? And we always have this random error epsilon as a Gaussian process, okay? So this reason this is the so-called Gaussian process model, okay? But in non-parametric regression, there is a powerful tools is the so-called functional ANOVA decomposition. Functional ANOVA decomposition essentially mimic the ANOVA decomposition in linear regression to decompose this nonlinear relationship eta. Okay, this y and all these x has a nonlinear relationship eta here. Okay, this eta is unknown nonlinear relationship. Okay, in order to get interpretable results, the functional ANOVA decompose this non-parametric function eta into some ground mean, main effect, two-way interaction, three-way interaction, and so on and so forth. These essentially mimic the ANOVA model in linear regression. And then this model can be estimated using these so-called penalized least squares. Essentially, the first term is a still least square part, and the second term is penalized the smoothness or roughness of this eta function with the smoothing parameter lambda here, and n is a sample size. Okay, this is a so-called penalized or least squares. Penalized least square can be optimized in the so-called reproducing kernel Hilbert space, because it's well known that most of the time series of function can be operated in Hilbert space, but for smooth function, this reproducing kernel Hilbert space has a very nice property, so that we can have interpretable result. Okay, it's not a strange outcome from the minimization. Anyway, by this so-called representer theorem, we know the minimizer has analytical expression. Okay, and the computation of this representer theorem is high because it's there are n plus m coefficient need to be estimated from this model. Okay, there are some d coefficients essentially try to represent the global trend, and this c coefficient is with respect to some local curvature of this function. Okay. Anyway, the computation of this penalized least square is in the cubic order of sample size. If our sample size is huge, and obviously this is a big problem. Okay. And so instead of using all these n bases, okay, we instead want to use a q basis. Okay. Q is much smaller than n. Okay. Once again, this is a subsampling idea. Okay. So if we use Q, then our computational cost can be reduced to n times Q squared if Q is much smaller than n. Okay. But the problem is how large is the Q. Okay. So we develop several methods. Okay. So once again, we suppose these there is these x1 and x2 is generated from these non-uniform distribution. Okay, if we use a simple random sampling, we may sample some points which may not represent the overall distribution of these x1 and x2. These are the two covariate or predictors. Okay. Using a method we developed some years ago is this so-called ABS, okay, method. It still doesn't work very well, okay. But using our design idea, okay, the design method, okay, essentially is using the experimental design approach. We can find, okay, the sampling points we sample. It's really well represented the original sample. Okay, so this the further details of this algorithm is presented in our biometric paper, and then you can take a look. Okay, so the ABS is presented in our 2015 biometric paper, and then this SBS method is presented in our more recent 2020 biometric paper. And if you want to learn the details, you can look at these two papers. Okay. And then by theoretical analysis, we can show that the computational cost of our SBS is just slightly bigger than n. So it's n to the power, roughly is n to the power of 1.5. Okay. So this is not as good as a scalable linear order of the sample size, but is much better than the original, the cubic order of the computation. Okay, so this is some theoretical analysis. Okay, and then in reality, we also face another challenge. Okay, that is when we applied our design idea to the data set. Okay. In experimental design, we always generate data points or design points from the unit cube, okay, from 0 to 1 and so on and so forth, okay. In some occasion, this is okay. That is, we normalize our data points so that it shrink to this unit cube, okay. But in some circumstances, and this is not possible, okay. So for example, this is a well-known data set in machine learning. Okay, the data points form into these two circles, okay, overlap the two circles, okay. how to use the design idea to generate a sample, okay? So the idea is the following, is first we map these data points into this unit cube, okay, into this unit cube. And then in this unit cube, once again, we apply the experimental design idea to generate the design points using this black triangle to denote it, okay, in this plot. And then we find the nearest neighbor of subsample data points, okay, using this red circle to indicate. And then once again, once we get this unit, this red circle, this subsample, we map back to the original sample, okay, and to get our subsample. We can see these represent this whole data set very well, okay. So the key technique is how to map this original sample from arbitrary distribution to a uniform, essentially to a uniform distribution. And then once again, from uniform distribution, we want to map back to this arbitrary distribution. Okay, the technique we use is the optimal transport. Okay, the theory of optimal transport is a rapidly developed field starting from early 2000. Okay, especially one of the mathematicians developed many novel theory for this field. Bienvenida got a Fields Medal. Okay, so make this field very well known. Okay, and has been many of the theory and the method have been borrowed to machine learning and the data science. Okay, the optimal transport is the original idea is proposed in 17th century, okay, by some probabilities. The original idea is very simple, is you have some manufacturer, okay, some resources you want to transport to some distributor, okay, and then what you want to do is want to find the minimum transportation cost so that you can distribute these resources to the distributor, okay? And to describe this in probability language, that is you have original distribution, we use mu to denote it, okay? We want to transform this distribution to another distribution, we use nu to denote it, okay? And then how to get this done in an optimal way, okay? The optimal way is defined as some cost function. This cost function can be L1 cost function, can be L2 cost function, and so on and so forth. This cost function denote the transportation cost, okay? Even though the name is a so-called optimal transport, okay, looks like a very empirical problem. And indeed, the original developer, the problem was proposed by the Monge, a French mathematician, and it's really a transportation problem. But now in modern probability field, okay, this is just a subfield of theory and the method, okay? There are tons of methods being developed in this field, okay? But anyway, the optimal transport works very well for the low dimensional data points, okay, for low dimensional data points. But in high dimensional data points, to calculate these optimal transports pose a significant challenge. And then in 2019, 2020, we published a couple of papers on this topic. Essentially, the first paper is we developed a more efficient technique to compute the optimal transport in high dimensional case. And then in the second paper, we realized, okay, if one is a high dimensional, the other is low dimensional, this is essentially a dimension reduction technique. And then we can use this optimal transport as nonlinear dimension reduction, and we show, and this nonlinear dimension reduction works very well. Okay, so anyway, as I said, these are the regional region we use this optimal transport is essentially as shown in the previous case. That is, we want to transport the arbitrary distributed data points to the unit cube, okay, to the uniform distribution from 0 to 1, okay. In this special case, then we can apply the experimental design approach to help us to select the subsample. And then once we select the subsample, we map back to the regional sample and hope this subsample can well represent the regional sample. Okay, so you can see there are many mathematical tools we can borrow to help us to achieve this goal. Okay, so let me summarize what I have been talked about for today's talk. We talked about several topics. Okay, we talked about the subsampling in linear regression. We talked about the subsampling in streaming data. We talked about the subsampling in misspecified model, and then we talked about the subsampling in non-parametric models. Okay, the technique we have been using, one idea we borrow is from the experimental design, especially the optimal design. Have many ideas we can borrow, okay, to help us to get a subsample, and a particular a little bit advanced probability technique or theory and method we have been using is the so-called optimal transport. This is especially useful because when the regional subsamples have some distribution, it's very hard to describe using the current distribution. And then we use optimal transport to transport these regional very complex distributed data to the uniform distribution so that we can apply the design of the experiment so that help us to select subsamples. Okay, so this is pretty much my talk. I would like to acknowledge my collaborator, Bienvenida from UC Berkeley, and Michael Mahoney also from UC Berkeley, and Tian Shram is my colleague, and Wei Biaowu from University of Chicago, Jianhua Huang from Texas A&M, and Nanzhang was his student, and many of my collaborator and my students in my lab, and it's also supported by the National Science Foundation and NIH. That's all for my talk. Thank you for listening. Any questions?
Okay, Professor, thank you for this interesting lecture. We want to know if anybody in the audience has questions, can raise their hand, and we can open the microphone. Okay, Professor, we want to thank you for this interesting talk, and we appreciate this time here in our symposium. We want to congratulate you for your hour that was given for the NSF. And we hope in the next year, when the symposium is in our presence, can you stay with us in our symposium next year, probably.
Thank you, really appreciate it. Yeah.
Okay.
I really enjoy it.
Thank you.
Thank you.
No sé si alguien tiene una pregunta para el profesor Ping Ma. Okay, Professor. Then we are going to give some instruction for all the audience and the participants in the symposium. And we appreciate again this effort that you are giving us for our event. And thank you very much.
Thank you. Yeah.
Okay, Lina. Queremos que por favor vamos a dar unas recomendaciones finales para todos los participantes. Por favor, Lina, nuestra asistente del simposio, nos puede regalar ok.
Una pregunta, ¿hay preguntas?
Jessie.
Buenos días, sí, señor. Sí, yo tengo una pregunta para el profesor.
Okay, Professor Ping Ma, there is a question, actually.
Okay, yes.
Vamos, Jessie, dale.
Okay, thanks. My question is, when I am working in a machine learning model with leverage points in regression model, what is the best technical in order to identify for these leverage points before I use machine learning? For example, in order to use other models different, for example, regression, robust with, let me think, please. Rich and lasso regression, for example, how can I identify the leverage points in these models?
Okay, yeah, very good question. Okay, so let me just talk about the answer the question to your last one. For example, if you want to conduct a lasso regression, okay, lasso is essentially you want to reduce your number of predictors to a smaller size so that you can fit a parsimonious model. Okay, actually we once thought of this problem. Okay, so in this way, you want to do two-way reduction in the sense you want to both reduce the dimension of your model and at the same time you want to reduce the subsample size. Okay, the sample size is reduced. Must be when you reduce the subsample size, you must consider, okay, what's the model? Okay, what's the lasso, how do you use the lasso procedure, especially, okay, what is this lasso parameter lambda? You want to, how do you tune this lambda? Okay, this is a little bit challenging question. Okay, so one suggestion, one study we have tried is that we can approximately fix this smoothing parameter or tuning parameter lambda into some ideal or sample size, or from historical knowledge, we fix this lambda. Once we fix lambda, and then we can still get some leveraging score like with what we did in the regular least squares. It's just you add a penalty term to this thing, and then we reduce subsample size. Once we reduce subsample size, and then we can apply this lasso procedure to this subsample. Obviously, this subsample must be larger than the dimension of your model. Otherwise, you cannot use the lasso procedure. Okay, but the key thing is you cannot let this tuning parameter lambda change during this process. Okay, if it changed, it may be result in different. You can result in some misleading subsample and then further mislead your variable selection. Okay, but this is our some pilot study preliminary analysis. We haven't published any paper, but I think it's a very good topic to have further study. Okay, this is a very interesting question, very important question.
Thank you, Professor. Thank you, Yesid, for your question. And we are going to finish. I don't know if any other question for the audience. Okay, Professor, we are going to finish we have finished the lecture. Thank you, and we are going to give some directions for our participants and for our assistants, Lina. Thank you, Professor, again, and see you later.
See you later. Thank you.
Lina.
Buenas tardes, buenos días, perdón, a todos ustedes. Nuevamente, agradecerles por asistir a nuestro evento. Quiero darles las siguientes recomendaciones. Por favor, llegar 5 minutos antes del ingreso de cada cursillo, conferencia, ciclo de comunicaciones y sesión de posters ya programados. Para cada cursillo ya se envió el respectivo enlace a los que ustedes ya escogieron. Por favor, en el momento de ingresar, hacerlo identificándose cómo se inscribió, con sus nombres completos, por favor. Estar pendientes, por favor, del chat, ya que en este se enviará el formato de asistencia para que, por favor, lo diligencien. A los ponentes de comunicaciones y de pósters, al ingresar a la sala que les corresponde, deben ponerse en contacto con los monitores para que ellos puedan darles los respectivos permisos. En estos momentos, ahora tenemos un receso y a las 11 podemos ya continuar con la programación. Muchas gracias. Los estaremos esperando.
Muchas gracias a todos. Vamos a dar por finalizada nuestra transmisión del evento inaugural. Muchas gracias a todos y nos vemos en las siguientes sesiones.